All right, so let's start with the answer to today's quiz. The question was, what is the dielectric constant? And let me remind you that dielectric constant describes how a substance behaves when it is inserted into an electric field. So if we have a certain established external, let's call it external electric field, and when we push in a substance into this electric field, that substance will produce its own electric field, and it will affect the resultant electric field. The new electric field, which consists of that external electric field and internal electric field, it's a superposition of those fields, is proportional to the original external field. And the dielectric constant is the proportionality coefficient. We have to divide original electric field by dielectric constant in order to get the new electric field. Before going to next subject, I would like to solve another example of typical application of I came up with a problem in which we will be able to use electric field vector and electric potential in order to find speed of particles in a device which is called an electron gun. An electron, typical application of an electron gun is in a cathode ray tube, which was for the last 50 years commonly used in TV sets. An electron gun has a filament from which, if metal is heated up, and it is, so electrons are capable to pop out from that metal. So from hot metal, from that hot filament in the back of the cathode ray tube, electrons are coming out and wander in the vicinity slowly. Now that filament is placed in a, well, kind of a can. It's a cylindrical, it's a cylinder with a hole on one side. And in front of this one there is a plate, also with a hole. And both this cylinder and this plate are made from a conductor, and they are connected to power supplier to produce appropriate potential difference. So there is potential difference between these two plates. Well, therefore, these two plates produce electric field here. And, well, considering that the distance is relatively small, it isn't on the drawing, but it is supposed to be that the distance is relatively small compared to the diameter, the electric field here is pretty uniform. Now, so from time to time, it will happen that an electron will get out through that hole. And see what is going to happen now with that electron. When electron gets out, that's immediately an electrostatic force is going to be exerted on it, because between these two items there is a strong electric field, and the force is going to push. It is designed in such a way, we want to design it in such a way that the force is to the right. Now some of those electrons may miss a hole in that plate and just go discharged through the wires, but some of them can get out. Oops, wrong color. Some of them can get out over here and travel with substantial speed. So this is how electron gun is built. Let me now ask you a puzzle. Potential, where potential is higher, here or there? Oh, at the same time you can think about it. Well, think about both. What is the direction of electric field vector between the plates? And, well, what are the shapes of equipotential surfaces? And which equipotential surface has higher potential, this one or that one? Yeah, because, I mean, since they are made from metals, so this metal constitutes one equipotential surface, this metal constitutes another equipotential surface. Now, I will give you something like 30 seconds to think about it, and you can even talk to each other. Go ahead for 30 seconds, find out what is the direction of electric field between the plates and which plate has higher potential. Go ahead. All right, let's vote. Let's start with electric field vector. Who thinks that electric field vector is to the right, consistently with the force exerted on the electron? Who votes for that? Who votes that electric field is the other direction, opposite to the direction of the force? Well, I see that the support for both ideas is comparable. How about other way, sideways? Who believes that way? That's good. Nobody thinks this way. All right. Well, the correct answer was that electric field vector is in this direction, because charge of an electron is negative. And recall that the force exerted on a particle placed in an electric field is equal to the charge of the particle multiplied by the electric field vector. Since charge of an electron has a negative value, then the force is going to be opposite to the electric field vector. Since we have the forces to the right, it means that the electron had to be to the left. Now, all right. So how about if we mark even electric field lines? So electric field lines are that way. All right. So where potential is going to be higher? So who believes that the plate has higher potential? This plate has higher potential than this plate. Who believes that? And here is higher potential and here is lower potential. Who believes in such a configuration? Nobody. Who believes that potential here is lower and potential here is higher? Well, there is some support for that, and that is incorrect. Potential here is higher. And now how to find it out? Well, how about if we just think about it? The differential difference in potential is opposite to scalar product of electric field and path segment vector. So let's say that I imagine a path that way. I choose differential segment this way. So let's find out for this fragment of a path, what will be the value of this product? Well, so we can take magnitude of this vector, it's a positive number, times magnitude of this vector, it's a positive number, times cosine of the two vectors. Now ds is in this direction, electric field vector is in this direction, so we have cosine of 180 degrees. Cosine of 180 degrees is -1, right? So we will get this product is negative. We multiply by a negative number, so we will get potential difference between, from this increase or change in potential from this point to this point is positive. And the same way, from this point to this point is positive. From this point to this point is positive. So we see that as we move to the right, potential is growing. And I can mark actually potential surfaces here. And they are getting higher and higher and higher. Actually, when you think, I don't really necessarily want to associate charge of a plate with potential, but in many cases it does work. Well, so in order actually to have electron to be pushed to the right, think what should be the charge of this plate and this plate. If this plate would have to be charged negatively, this charge positively, which actually the electric field lines indicate that, right? Because electric field lines, if we draw them, their orientation is from the positively charged object toward the negatively charged objects. So, indeed, this one has to be positively charged, and if it is positively charged, it has to have higher potential than the other one. All right. Well, in a typical cathode ray tube, this potential difference here is of the order of 1,000 volts. Why don't we algebraically solve for the speed with which electrons leave the gun? And I want to do it both ways. I want to use concept of potential, and I want to use concept of electric field vector. Both ways, we can solve it both ways. Why on the left-hand side we solve it with considering potential. So here is from potential. According to work energy theorem, change in kinetic energy of the electron is equal to the net work done on that electron. We can assume that in this situation the only significant interaction is due to that electric field. So the electric work is going to be equal to the net work. How about if I write it down that way? And this one is supposed to be equal to the change in kinetic energy of the electron. Now, which change between which 2 points? This point where it barely moves, and this point where it acquires already high speed. So for simplicity, let's approximate that kinetic energy here is 0, that it barely moves. So in principle, I should also say approximately. So initial kinetic energy is 0, and well, we don't know the final, and actually we are looking for that speed. So this speed is our unknown, and this is only unknown on the left-hand side. We can find out what is the mass of electron. 2 is a number, so we are looking for this speed. All right, now how about on the right-hand side? If we knew the distribution of potential potential in space, we can quickly find out electrical work, because this is conservative work. Conservative work is opposite to the change in potential energy. And so how about if I write it down here. Now I copy minus, and change in potential energy means potential energy at this point minus potential energy at this point. If I knew potential over here, I need just to multiply that potential by the charge of the electron to get potential energy here. In order to get potential energy at this point, and when I'm calculating change in potential energy, I have to subtract it. I need to multiply charge of the electron, which is opposite to the elementary charge, multiply by potential at the second place. So if I recalculate that, I mean, if I bring this minus over there, I will have here just elementary charge multiplied, and what will be left will be V plus minus V minus, and let's call it that potential difference. So from here we can solve for speed. So we need to multiply this expression by 2, divide by mass, and take square root of it. So you saw that knowing potential leads to work, and from work, if I can find out work, I can use work energy theorem and compare it to kinetic energy from which I found the final speed. All right, let's now go to the other solution from electric field. Well, first I would have actually to find out what is the value of electric field. We know that electric field is going to be to the left. However, what is its value? And well, we know distribution of potential, so from that I can find out electric field, because electric field is opposite to the gradient of potential. Now, how about if we introduce here that this is x direction, and we recognize that y and z components of electric field vector are 0, so let's concentrate only on the x component of electric field. So x component will require that we calculate derivative of potential with respect to x. Now here we have electric field which is uniform, which means that potential increases. I mean, potential as an electron moves from this point to this point, potential increases at its location at a constant rate. In a uniform electric field, the separation between equipotential surfaces are identical. Yeah, so if I have, let's say, by 1 volt, so another 1 volt and another 1 volt, separation between those plates is going to be the same. I could also say that potential is a linear function of position here. And so let's say that this is x, and this is potential at x. Potential changes like that. So what will be the derivative? Oh, how about if I think about, let's say that the separation between the plates is d. So here is potential on this side. I assume that this is my reference for potential, so I assign potential 0 to that side, which I marked here. What would be the value of potential at location D? And so this V minus equals 0. V minus is equal to 0 volts. Now V plus is equal to how many volts. Potential at this point will be related to that number. How? Well, it will be exactly equal to that number, right? So at a distance d from the left-hand side plate, potential here is delta V. So what will be the value of this derivative? Now let's recall the definition of derivative. What is derivative? What is it? Right. It's tangent of the slope of the slope of the tangent line. Well, not one, but well, we can see that at each point the slope of the tangent to this line has the same value, which means indeed that electric field vector is a uniform function. And not only that, but if I know what is the separation between the plates and what is potential difference between the plates, I can say what is that slope. It happens that for this type of a function, derivative is equal to the difference quotient. So if I want to find out derivative at this point, it is equal to a difference quotient, any difference quotient. Therefore, I can write down that this is equal to this difference quotient. Right? That slope is going to be equal this distance divided by this distance, or this value divided by this value. So coming back over here, and indeed this is true, I can write down that the component of electric field vector is equal to potential difference between the plates divided by the distance between the plates. All right, I will erase now this mathematical digression and solve a problem like now the problem is reduced to to a problem of finding the speed at which an object is going to hit the floor. It's exactly the same problem now, because since I know what is the what is the value of electric field vector, I can find out the force. So x component of the force is going to be equal to charge of the electron multiplied by the value of the electric field vector. So it's elementary charge, difference in potential divided by distance. This is force. If I divide now this by mass, it's better to put m in front of d, because otherwise one can think that it's a differential. What am I going to get? Acceleration, correct. It's also approximately and the assumption that the electrostatic force is the only significant force. All right. So now let's find out how fast it is the electron is traveling here. Well, if I know acceleration, I will have to know when electron is going to be at this point. So let's say that I consider that instant zero is when the electron gets in the hole. So if electron gets in that hole, then it will be a simple expression for its position, because then at instant t, position is going to be just 1/2 of acceleration times t. And well, so it is going to be at location d, let's say at instant T1, which means that this T1 is equal to D divided by AX. All right. Now, in order to find out what is the speed at that location, I have to multiply it by acceleration. So speed at this location is going to be AX. So which means AX and AX cancels, which means that that speed is going to be, oh, I'm circling. Oh, square. So, so here is wrong. Which means that over here, oh, let's find out this T from here. And so T1 is equal to D divided by AX and square root of that. So the square root of 2D divided and AX, we found AX over there, E delta V times, there is something, I'm messing up something. Can you find out what I'm doing wrong? I mean, it's algebraic mistake. A what?
So that means 2D squared.
Yeah.
W.
2D squared and over E over.
Over here?
The next term over. Because you replace AX, which should add more terms than just E over.
Well, yes, but I mean, I see that it is wrong way. Yeah, because I mean, that one is correct. So I know that I'm supposed to get the same value. Where did I make a mistake? No, that one is fine. However, I mean, it's a complicated way. Why don't we go first simplify it here? Yeah, so from this I can write down that T1 is equal to D divided by acceleration and square root of it. That's correct, right? So now I will plug in here. Now this is AX times square root of 2D divided by AX. So let me bring this AX into square root. So the result will be 2DAX. Oh, let's put it the other way. 2AXD. All right. And now let's plug in for AX what we found here. So it will be 2 and AX is elementary charge times potential difference times distance between the plates divided by mass and distance between the plates. All right. Now I'm happy. And you should be happy too. Why? It's the same, right? No matter how we solved it, we got the same speed. Which solution was simpler? Using potential. And do you know why? Yeah, because now when actually, because over here we really used Newton's law to relate acceleration with force or motion with interaction. Here we related motion with interaction at this point using work energy theorem. And, well, usually it is, which solution is easier depends how you know the interaction. Do you know how it changes with location, or do you know how it changes with time? When you know how something changes with time, it's easier to use Newton's law. If you know how potential energies at various points, then it's easier to use the work energy theorem. All right, so this will be all for digression. I would like now to talk about discuss operation of a device which is made by using plates. It's not the first device which is in electronics discussed in this class, although we do not really spend much time on the other one. The other one is a wire. And a wire, since it is a piece of metal, it has everywhere, an ideal wire will have everywhere the same potential. Along a wire, we should have the same potential. We'll see, this would be an ideal wire. We don't have an ideal wire, and every wire is another device which we will discuss after capacitors. But for a moment, think that wire is an ideal wire, and potential along a wire has the same value. A capacitor is an electrical element which has two sides. These sides are called plates. Although very rarely they have a shape of a plate. They usually have other shapes than plates. Nevertheless, they are called plates. So think about it that this is one plate and this is another plate of a capacitor. In a capacitor, potential difference between the plates is proportional to the charge transferred from one plate to another plate. Here we have the relationship. Charge transferred from one side of the capacitor to the other side of the capacitor is equal to the potential difference between the two plates. Proportionality coefficient relating charge transferred with potential difference is equal capacitance of the capacitor. On electrical diagrams, you can find this type of a symbol, and this symbol represents a capacitor. Now, let's relate precisely how that relation should be interpreted on a drawing of a capacitor. So if we charge capacitor, we move charge from one plate to another plate. Note that the total charge on the capacitor is 0. You never really change the charge of the entire capacitor when you charge it. Charging a capacitor really is not the same as charging a rod, when I was charging a rod by rubbing it. Charging a capacitor means that you transfer charge from one side of the capacitor to the other side of the capacitor, and you don't change the charge of the capacitor. Therefore, actually, even in the technical language, when we charge the capacitor, we don't say that this is charge of the capacitor, but we say that this is charge on the capacitor. So never say charge of the capacitor. Charge on the capacitor. And charge on the capacitor means that it is transferred from one side to another side. All right, so if we transfer charge from this side to this side, note that this Q refers to charge on one plate only. The other plate has opposite charge, so the other plate has charge minus that value. It's proportional now to appropriate potential difference. It has to be from the potential at which we have charge Q, we have to subtract potential of the other plate. If you are consistent in calculations, then no matter how you do it, it will work. However, it's very easy to make an error. Why don't I go to the whiteboard and show you an example? All right, so let's say that we have a capacitor. Why don't we think that this is a capacitor which has capacitance of 1 microcoulomb. And I connect it to a voltage source, to power supply, and create potential difference of 5 volts between the two plates. So why don't I choose this as my reference for potential? So potential of this plate is going to be how much? How much? 0. So potential of that one will be 5 volts. Let's make it here. All right. So, what will be the charge on the capacitor? Shout. Not 5 volts. 5 volts is potential difference between the plates of the capacitor. My question is, what is the charge on the capacitor? How much? Christy, shout. 5 volts times that coefficient, the capacitance, correct. So 5 volts times 1 microfarad, I meant. Capacitance is measured in farads. Times 1 microfarad. This will give me answer in SI units of charge, which means coulombs, or precisely microcoulombs. So it will be 5 microcoulombs. The charge on the capacitor is 5 microcoulombs. Have 15 seconds now to consult with your neighbor. How is it charged with this 5 microcoulombs? Where is that 5 microcoulombs? All right. Who believes that 5 microcoulombs is between, the charge of 5 microcoulombs is between the plates? Yeah, in this space over here we have charge of 5 microcoulombs. Who believes this? I'm glad that nobody does. Who believes that 5 microcoulombs is on each plate? Who believes this? Those of you who believe this, you are wrong. Who believes that 2.5 is on each plate? Those of you who believe that way, you are wrong too. Who believes that 5 microcoulombs is here? Those of you who believe that, you are wrong. Who believes that 5 microcoulombs is here? Yes, this is correct answer. All right. What is the charge of the other plate? Minus 5 microcoulombs. Correct. Minus 5 microcoulombs. All right. Now let's say that I will set up a similar problem. Potential of this plate is 0. Potential of this plate is 5 volts. The capacitance of the capacitor is 1 microfarad. And I want to find charge Q. I want to find this charge. Yeah, because previously, I mean, I know that over here you thought that this is Q, this is minus Q. Now I made a mistake of labeling, and I labeled it that way. Because in principle, I didn't have to know that it's 0 and 5. How about if I just think about it that way, that this is 1, 2. Right, so now if I think that this is potential of plate 2, this is potential of plate 1, then consistently with the drawing on the screen, I should write down that this charge is equal to capacitance, which is 1 microfarad, multiplied by potential difference between these two. And now potential at this one is 0 volts. Potential of the other one is 5 volts. So what will be the result? Negative 5 microcoulombs, which means that Q is equal to negative 5 microcoulombs. What is Q consistently? 5 microcoulombs. So you see this pipe, actually I inverted the formula, and I picked Q to be lower than minus Q. When I solved for explicit values, I got the same result as this way. As long as I'm consistent, I'm going to come to the correct conclusion. Very often, actually, you will see symbol for potential difference as just V. And make sure that you do not confuse, because now you will have to recognize if in the formula V refers to potential or to potential difference. If you are confused for a while, then for a while don't use symbol V, but put delta V. Delta V will refer to potential difference. When you get comfortable, and it will be obvious for you if you need potential or potential difference, then you can come back to this notation. All right, so coefficient. This coefficient is called capacitance, and the SI unit of capacitance is 1 farad. And I think that this will be right place to finish the